Hello, my name is Fernanda Grande and I'm a nutritionist working on food composition for more than 12 years and since 2015 as a consultant on food composition at FAO. First of all, I want to say thank you to the organizers for the invitation to this important Aero-free workshop and also to the Food and Nutrition Division at FAO, especially to Bridget Holmes for giving me the opportunity to present today. So in my presentation, I will show my experience as a compiler collecting and calculating protein and amino acid data following FAO and INFOODS standards and guidelines. So my presentation will cover a brief introduction regarding the recommended methods for protein analysis, a comparison of the preferred and acceptable methods, the problems with the general assumptions when we use the indirect methods, and challenges when compiling protein and amino acid data, and at the end I will give you my key messages. So protein is a component included in all good food composition tables, since it's part of the approximate composition of foods, which is the most basic information in food composition tables. At first, we may imply that this is a simple component, since it's very common in food composition tables. However, there are some important issues that I will introduce here in my presentation. To start, let's just quickly recap what proteins are. So proteins are made up of chains of amino acids, meaning that the amino acids are the building blocks of proteins. So the amino acids are organic compounds that contain one amino group, including the nitrogen, and this is what differentiates proteins from the other macronutrients. They also have a carboxylic group, along with a side chain group represented here by R, which varies and is specific to each amino acid. So to form proteins, the amino acids need to be combined, and this happens when the amino group of one amino acid connects to the carboxylic group of another amino acid, just as highlighted here. So when they are linked, the reaction releases one molecule of water and the peptide bond is formed linking the amino acids. So if we want to quantify protein in foods, we should do the other way round. We should hydrolyze proteins to their component amino acids, which can then be quantified. The sum of the amino acid residues will represent the protein content of the food, in this case measured directly by weight. This should be the preferred approach to quantify proteins in foods. This is also what was recommended in 2003 in the FAO report on food energy, methods of analysis and conversion factors, which discussed a number of topics related to the various methods of analysis for macronutrients in foods and the energy conversion factors used, including some recommendations. In the chapter 4, the report includes a summary of the recommended analytical methods for all the energy-yielding macronutrients. And for protein, they recommended that the preferred method is the sum of individual amino acid residues. So in this case, the food composition tables should reflect protein by the sum of amino acids whenever possible. But the report also states that until values for protein based on amino acid analysis are generally available, the indirect analysis performed by measuring the total nitrogen content of the food, which is then multiplied by a conversion factor, is also acceptable. However, most or nearly all food composition tables use the indirect method to report the protein content in foods, and this is a consequence of the different analytical approaches. To perform the sum of individual amino acids, which is the preferred method, the protein can be hydrolyzed to their component amino acids, which can then be measured by different techniques, just like ion exchange, gas liquid, or high-performance liquid chromatography. As we saw, this is considered the most precise method to calculate protein content of foods. And the main advantage of this approach is that it requires no assumptions or knowledge about either the non-nitrogen protein content of a food or the proportion of nitrogen in the specific amino acids. And these are the problems with the use of the nitrogen and the conversion factors which we are going to discuss. But on the other hand, its disadvantage is that it requires more sophisticated equipment than the methods to analyze total nitrogen, so it may be not feasible for many laboratories. And also, experience with the method is important, especially for some amino acids such as tryptophan that are more difficult to analyze. So these are the main reasons why this method is still not widely used in food composition tables. The quantification of total nitrogen in foods is traditionally determined by the Kildall technique in most of the cases, or also by the Dumas technique. I will not go into details on the methodologies, but it's important to mention that they show good agreement. But in both cases, they will give us the nitrogen content in the food. And since we know that the main source of nitrogen in foods in general is protein, by applying a conversion factor, we can calculate the protein content in the food, in this case, indirectly determined. By calculating protein based on nitrogen following this approach, some assumptions are needed. So initially, when this method was created, the average nitrogen content of proteins was found to be about 16%, which led to the use of the conversion factor 6.25 to convert nitrogen content into protein content. This 6.25 came from the calculation of 100 divided by 16. This first assumption was based on the comparison of a few proteins, mainly from animal origin. Then, when we decide to calculate the protein in foods in grams by multiplying the nitrogen by the 6.25, we are assuming that all nitrogen in the food material comes from protein, and this is the second assumption. But the problem with this assumption is that first, non-protein nitrogen is also found in foods, for example as part of nucleotides, creatine and choline. And some foods are rich in non-protein nitrogen, just like some types of fish, many shellfish and crustaceans. And second, the nitrogen content of specific amino acids as percentage of weight varies according to the molecular weight of the amino acid and the number of nitrogen atoms it contains. Based on these variations and also considering that the amino acid composition varies among proteins, the nitrogen content of proteins will also vary. In response to these considerations, Jones, 80 years ago, suggested that the conversion factor of 6.25 should be abandoned and replaced by specific conversion factors for the foods in question. So he evaluated the nitrogen content in proteins for some foods to try to propose conversion factors that could result in better protein values than those calculated by the use of the general factor of 6.25, which was used until that moment. And these are the specific factors proposed by Jones as in the original publication. And here again, as in the original publication, but in a more readable format. These factors now are referred as Jones factors, and they range from 5.18 for nuts and seeds until 6.38 for milk. These factors have been widely adopted and were also used by FAO and the World Health Organization in the review of protein requirements in 1973. And they are also recommended for use in the FAO publication for food energy from 2003. So regarding the indirect analysis of protein, The report says that a specific Jones factor for nitrogen content of the food being analyzed should be used to convert the nitrogen to protein when the specific factor is known. So when we don't know the specific factor, we can use the generic 6.25. The Jones-specific factors are also recommended for use in the FAO INFOODS guidelines, with a few complementary factors from other sources as indicated in the document. As a food composition data compiler, I have compiled and calculated protein and, in some cases, amino acid data for the food composition tables listed here. The approach used in all cases was the indirect method, using total nitrogen values and a specific conversion factor as recommended by FAO INFOODS whenever possible to calculate the protein content in the different foods. I will use the FAO INFOODS Global Food Composition Database for pulses as an example, but the methodology and challenges are the same for the different databases. So the pulses database was one of the legacies of the International Year of the Pulses declared in 2016. To prepare the final user database, which is available for download on the INFOODS website, almost 1,000 references, mainly scientific articles, were scrutinized to collect the information for 23 species of pulses. References with the required information were compiled, resulting in an archival database with approximately 2,600 food entries and about 34,000 data points. These data were the basis for the data aggregation and preparation of the final user database. As expected, most of the compiled data refers to proximate composition. Since protein is usually analyzed as part of the proximate composition, 74% of the food entries compiled included data for protein, the majority referring to nitrogen analysis. There were no data for protein calculated based on the sum of amino acids, and for a few foods, the analytical method was not precisely described in the original publications. But for about 30% of the protein values compiled, the conversion factors used for converting nitrogen to protein were not available. And this may be an issue since it can vary among the publications, and we could note from the information compiled from the original references that the conversion factors reported ranged from 5.3 to 6.25. But according to the Jones-specific factors, here from the FAO INFOODS guidelines, pulses correspond to bean, and the 6.25 conversion factor should be applied. Therefore, in this case, it is important to recalculate all the protein values according to the standardized specific factor. Here you can see the reference database for the pulses database, where the values were standardized. Note that in this column where the conversion factors from nitrogen to protein were different from 6.25, all proteins values were recalculated in the standardized protein column. First, the protein value compiled from the original source was divided by the original conversion factor to result in the total nitrogen content. Then, the total nitrogen was multiplied by the appropriate conversion factor, in this case 6.25, to obtain the standardized protein. This approach is fundamental to present standardized values for protein in food composition tables. It's also important to document all the conversion factors used in the database. Here you can also see that each component in the database was linked to the respective component identifier from INFOODS, the tag names, in the first line of the Excel file. The tag names are unique codes or abbreviations that allows to clearly define components using a few characters. The primary use of tag names is to determine whether the associated values can be compared or combined. But as I just showed, since protein is a calculated component, it's also important to check the conversion factor used in the calculation. In this slide, we have the main tag names for protein. The three tag names in the left should be used for the indirect method, where we have total protein calculated from total nitrogen. On the right, the first two tag names refer to total protein calculated from protein nitrogen, and the last tag name should be used when the analytical method for total protein is unknown. In addition to protein, amino acid data was also included in the POSAS database. As most of the food composition tables, data for 18 amino acids were included. The data aggregation for amino acids was performed with amino acids expressed as milligram per gram of nitrogen, just as presented in this slide. The use of the nitrogen content of each sample as the basis for expressing the amino acid content eliminates the variations among the samples of a food due to different levels of protein or other components such as moisture or fat content. It also facilitates comparing the values among the different sources and borrowing any missing value for a particular amino acid. Therefore, in this case, the amino acid content was calculated from the amino acid profile in milligram per gram of nitrogen to the actual content in the food, considering the total nitrogen content. So, in the main table for users, the amino acid data was also expressed per 100 grams of edible portion, just like the other components. The data for amino acids were much more limited in the literature when compared to protein data. For the foods in this slide, we can see, for example, for the last food that is cowpea, that up to 41 data points were available for some amino acids during the data aggregation. But here, for other pulses, the number of data points were very limited or not available, just like for the last food here, nave beans, where the amino acids were borrowed from the generic common bean, since no data was available for this particular variety of bean. It's true that amino acid analyses are less frequent in scientific articles compared to protein data, but also in many cases it's difficult to compile the few amino acid data available because the denominator is not clear. It's very common to read in the publications that amino acids are expressed per 100 grams, not making clear if it's per 100 grams of edible portion or of dry food or even per 100 grams of protein. So, given these uncertainties, in many cases data for amino acids cannot be compiled. So, to summarize, based on my experience, the key issues for compiling or calculating protein and amino acid data are related first to the conversion factors. So, the specific conversion factors from nitrogen to protein should be used whenever possible. The protein values compiled from the literature should always be standardized in terms of conversion factors used. Also, the conversion factors should always be documented at least in the reference database. Additionally, the tag names should always be included in all levels of the database to precisely identify the components. And for amino acids, the data aggregation should be performed using the amino acid profile expressed on nitrogen bases. Well, that's all for my presentation. Thank you for your attention, and I hope that this presentation was useful for the discussions in this workshop.